Hey guys, we are going to be going over two-way ANOVA and chi-square tests today, starting with number one for the lab assignment. We're going to look at two-way ANOVAs, and here the question is asking us if age and gender have an effect on income. So age and gender are going to be our independent variables, and then income is going to be our dependent variable. And it's a two-way ANOVA because we have two independent variables. So the question is asking us, is there an interaction effect between age and gender in predicting outcome? And then to report the F-test, the effect size, which I'll explain in a little bit, and whether the significant age effect, um, if there was a significant age effect, to conduct the ad hoc test to determine where that difference was coming from. So that'll all make sense in just a second here. We're going to use JAMOVI as per usual to run the test, create an interaction plot, and then I'll go over an APA style response as well for two-way ANOVAs. So first, we are going to import our data set, and it is career. I'm just going to delete these columns so you guys can see everything. And then we have all of our variables here, right? So we are going to run an ANOVA, and it's going to be a two-way ANOVA. Our dependent variable is going to be income. Let's just use income 1. And then our fixed factors or independent variables are going to be age and gender. And then we want the partial eta square. And then we'll get into the other buttons in just a little bit. But for the sake of simplicity, let's look at this table first so we can interpret this ANOVA. We can see that there was a main effect of age on income as evident by this significant p-value. And then we can see that gender also had a main effect on income, but there wasn't an interaction effect here between age and gender in predicting outcome, as evident by the p-value here. It's above 0.05. So with that being said, we know that we have two significant main effects, and we know that they're responsible for a certain percentage of variation in the dependent variable. So for example, age would be 8.5%, or actually, let me say that again. 8.5% of the change in income would be due to a person's age. And then for gender, 7.5% of the change in income would be due to the person's gender. So basically it's saying that age and gender affects income, and then the eta squared values will give you like sort of a percentage, um, just to kind of contextualize that stuff. But more importantly, it represents the effect size. And the reason why the effect size is important is because we can see that this is significant and this is significant, but we don't necessarily know how significant it is. In order to see like the magnitude, in order to determine the magnitude of significance, we need to pay attention to these eta squared values because they tell us exactly how significant it is. Like these are both significant at the 0.001 level, but then they're responsible for a certain, like one is responsible for more change in the dependent variable than the other. So that's important to note. Um, just for fun, so being that the interaction effect wasn't significant, we can just look at the main effect here, the different levels of the main effect. But generally speaking, if this interaction term was significant, this interaction term would supersede the main effects. So in your answer, you would just talk about the interaction term, and then go to the post hoc and then try to find out like where these differences were coming from in terms of like what level, what age, band, and what gender, in this example, male and female, um, the levels of each variable, which levels of each variable are interacting with one another to produce the effect that we're seeing. But we don't really need to pay attention to the interaction term. for this example because it's not significant. So now, I guess we don't need to do assumptions here for all intents and purposes. We need to run the post hoc test. And these tables are going to look a little bit formidable, but it proves the point. Um, let's do a Bonferroni correction, which is a bit more stringent than the Tukey. So now we can see like all the different levels of the age variable being compared to one another. So I believe it was those at 29 and under are significantly different than those 30 to 39, 40 to 49, 50 to 50, or 50 plus. And we can tell because it's significant here. And this is significant. And then gender was also significant. There was a significant difference between males and females. But there's a better way to kind of visualize these differences aside from looking at numbers. It's a bit abstract here to interpret. So let's plot these terms based on the marginal means that we see. And once this page, there we go. Oh, so this is important. This chart would represent the interaction term, but the interaction term was not significant in this omnibus table. So this is not significant, right? So we don't need this. We need to plot these interaction terms individually in order to be able to like visualize these differences a little bit better. This is easier to look at basically is what I'm saying compared to this. But you need to use this post hoc test to look at and see where the levels are coming from or where the differences are coming from within the levels of the independent variable. So we can see there's a significant difference. You'll see the same things on the post hoc comparisons, significant difference between 1 and 2 and 2, 3, and 4, and then significant difference between gender. So when we're writing our answer in APA, this is kind of what it's going to look like. So this is the test that we ran, the two-way and between subjects ANOVA, and then we looked at the impact of age, and then you have to give all of the different levels of the age so that the reader knows what you're talking about. And then the gender as well is our second independent variable, and then we have both levels. And then we used income as our dependent variable. So results suggest that both age, I'll have this side by side so you guys can see what I'm talking about. So results suggest that both age and gender had significant main effects on income. There was no interaction term. We just saw main effects. And then when we're giving our answer, it's sort of similar to the t-test, but with the addition of the other degrees of freedom. And then you give the F statistic, and then you give the level of significance, followed by the partial eta squared, which is very important. And then we can say gender did not have a statistically significant, interaction with age in affecting income. And then we can still give that formula here just to show the reader like this was not significant. The interaction term was not significant. And so we conducted a post hoc test, which would be the simple effects analyses were conducted using the Bonferroni correction. So the Bonferroni correction is just a really strict like statistical correction because it'll help you avoid making type 1 and type 2 errors. So because we don't want to fish for a significant effect if it's not there. That's kind of what alpha inflation is. like in the simplest form. So again, simple effect analyses. This was just the post hoc correction for family-wise alpha inflation suggests that males earn significantly more than females, and that individuals under 30, so that's these guys right here, earn the least, followed by people in their 30s, which would be age 2, with individuals in their 40s and 50s categories generally earning about the same regardless of gender. So right here. And although these do look different, again, we can go back to the post hoc table and see like the difference between 3 and 4 for age was not significant. So although you see differences here in the graph, it's not reflected. It's not reflecting significance. They're not significantly different. Um, and so we saw these two main effects. We essentially described these two graphs for the post hoc test, and that's basically all you need to do. Alrighty, guys. So now we're going to run a chi-squared test because from the two-way ANOVA, or from ANOVAs in general, we know what to do when we have a categorical to a continuous variable. But what do you do when you have a categorical variable, when you're trying to compare two categorical variables, I should say? Um, so we're going to be looking at question number 2. Were juniors and seniors more likely than freshmen and sophomores to attend review sessions? And then year is categorical because we have juniors, seniors, freshmen, and sophomores. So we're comparing groups categorically. And then we have the review sessions. So did they attend the review session or did they not attend the review session? And then we have our hypotheses here. Make sure to state them, that the class level and review attendance are independent from one another. That's the null. And then the alternative hypothesis is that the class level and review attendance are not independent of one another. And I guess you've kind of got like a sneak preview here of the contingency table, but I've already imported my data set, the students Excel file, it'll be on Blackboard, into JAMOVI. And now we're going to run a chi-square. So we'll go to frequencies, we'll go to independent samples, and then we'll throw year, and then review. And you can see here right away, this table looks a little bit different. This table looks a little bit different from this table, right? So we can solve that problem and make this table a lot easier to read by just switching these variables around. And we have a 95% confidence interval because the question asked us to use the 0.05 level of significance. Our hypothesis is good. We're not predicting a direction. We're just saying it's independent or dependent on one another. And then you can even look at, if you really want it to be fancy, like the expected, kind of like what you did in class with calculating observed and expected frequencies. This is basically the point of a chi-squared. But for all intents and purposes, we are going to learn the basics today of interpreting significance. So let me just actually check this and move it. These observed counts are just what was already in the spreadsheet. And then we're going to definitely need to do a bar plot so that we can visualize these results. We'll make it easier to explain. But you know what? Let's actually just interpret the results first. So this is our contingency table. We've seen this before. This is the output of our chi-squared test. So we have our chi-squared value, we have our degrees of freedom, and we have our p-value, which is telling us it is not significant. So class level and review attendance are independent of one another. This is a non-significant result. This table is going to be important because you'll be using it in your results. But before we get into the results, let's just look at how to plot a table really quickly, or a bar plot rather. Um, so I would just stack them to make it easier to interpret. I mean, we would interpret it based off of the chi-square table, but this helps us kind of visualize it. Like, although if you just looked at this plot alone, you'd be like, oh, there's a marked difference between going to the review session, not going to the review session, and going to the review session. And then also like the proportions of the years of students and how it's kind of similar over here. Um, just looking at this table alone, again, is not going to tell you what what's going on with the data. Like you have to look at the quantitative aspect of it to know that it's not significant, so that you know what you're looking at over here. So make sure to copy and paste both of those onto the assignment sheet, and this is how you'd write the results out. A chi-squared test of independence was performed, so the name of the test, and then what was your test looking at? We examined the relationship between class level and review attendance, and the relation between these variables was not significant. Again, this is our P, not significant. So chi-squared, the degrees of freedom, we have our N, like the number of people in the sample. The reason why you put the N in the answer is because chi-squared is really sensitive to sample size. Um, so it's helpful for the reader to know how many people were in your sample in case, for whatever reason. We have the chi-squared value, and we have the p is greater than 0.05 because it is greater than 0.05. So then we kind of have a sentence to say what this equation means, this formula means. Um, Attendance was independent of class standing. Therefore, we fail to reject the null hypothesis. So it's as easy as that. I think number one is probably going to be a little bit more difficult just because you have to interpret these post hoc comparisons. But it's easy once you have the graphs. So look at the omnibus table. If something is significant, look at it in the post hoc, then create a graph so that you can visualize things. And then same thing with the chi-squared, except we don't really have post hoc comparisons with the chi-squared. Um, and that's pretty much it. See you guys in the lab. Let me know if you have any questions.